I will emphasize one thing, though, and something that I gained an appreciation for when we got involved by funding the Rad Lab with Dave, is how effective David and his team have been in engaging with industry in general. It's sort of been a very productive relationship that they had in the way they interact with them. And with us and people like ourselves, and I encourage you guys, if you're interested in these, to reach out and look for opportunities for collaboration as well. So without further ado, I'm going to let Dave talk. Dave, I just have to mention one last thing, that your slide title and the abstract sounds a little bit like a Stephen Colbert sort of rant to some extent. So I'm wondering if you're actually claiming that CMPs or multicores are destroying America in one way or the other. But David Patterson.
All right. I'd like to thank Google, despite its Stanford origins, to starting on Berkeley time, which is 10 minutes after the hour. It's making me feel welcome here. So this is our logo, and kind of as you'll see, for several years we've been talking about this internally, and we decided that we could think of the problem as the parallel hardware as one of the towers, and the parallel software as the parallel applications another tower, and we had the software span to connect them together, and the more we thought of it, that looked a lot like the Golden Gate Bridge. That's the view from Berkeley, and then there's the users in Marin, and then the valley down here has got the industry. So we got to connect the users to the industry via applications and software. So I'm going to talk quickly about how we got here, and that's a bunch of the points here, especially for this student. Spend more time about the Power Lab, and then despite the starting time, Luis promised I could talk about this brand new performance model, which will be a more technical, in-depth thing for people interested in the lower layers of the software layer and architecture, of a pretty simple way to get some insights on whether your program and your architecture is running as well as it hoped. Brand new slides here. So how did we get here? We ran out of power. It was amazing to me that every generation we could use more power, and nobody said anything with microprocessors, and now they say it. You don't get any more power, so there was nothing they could do, and this was a surprise to the computer industry. And this illustrates this surprise. There's something called the International Technology Roadmap for Semiconductors, which includes all the semiconductors companies in the world, and they get together every 2 years and say what's going to happen in the next several years. So this is a plot of clock rate over time, and by now everybody's of course using 10 gigahertz processors, and next year it'll be 15 gigahertz, and so that was 2005. Just 2 years later, the roadmap slammed down. So this was a surprise. Apparently the people just had blind faith that we're going to overcome these obstacles we always had, and the clock rates would keep going up. So that slamming down means that we've jumped to multi-core, not because of any breakthroughs in computer science. It's the only way we could imagine getting more performance given the power limits, and which kind of stepped on the third rail for computer architecture was, well, I've got this great idea for a new computer. You just got to train all the programmers in the world to do this new thing. Well, that's actually what the industry bet is. And so, maybe evolution and global warming's controversial in some parts of scientific computing, but I don't know any computer architects who aren't saying that the future is parallel. And by the way, all the companies that build microprocessors have their next 4 or 5 years of products underway, and they're all parallel. So we're on our way. And those of us who know our history know that, this is a pretty sad history in parallel computing. Occasional advances, but a lot of failures. And there's a whole lot of companies, some of whom have led to wonderful buildings in the Silicon Valley area, that at a time, parallel computing looked like a very promising thing to do. So what's going to happen if the PCs of the world, the laptops of the world, if everybody who's got, say, 32-core laptop or PC, and your friends ask you, should I buy the 64-core laptop or PC? And because, should I do that? And if everybody in the world says, no, there's no software that you care about that will run on 64 cores any faster than 32 cores. So the two interesting things about that statement, it seems like I would bet a lot of money that that's true, right? I'd bet there's no way a 64-core laptop is going to run anything that anybody cares about faster. Almost nobody that would be true. At the same time, if that's not true, for the industry, the way that we're going to get Moore's law of faster processors is to use more cores. That's going to be a bad thing for the industry, and maybe the actual blue part of the line is the actual growth of PCs. Would we see this falling down of sales of PCs if computers didn't get any faster anymore? That's been kind of practically Moore's law for most people, has been higher clock rates, which they associate with higher performance. There's no more higher clock rates. Will there be actually higher performance? You know, that's to be determined. So is this really an interesting problem, or are we just, because we're friends with industry, working on doing their dirty work for them? So let me quote 3 different sources. Our good friend Jim Gray, a completely opposite end of the spectrum. The Gartner Group recently said, what would be big problems to solve? And then John Hennessy's quotes. So Jim, who was lost, a good friend of many of us, lost at sea almost 2 years ago. When he won the Turing Award 10 years earlier, his #1 problem, he looked at all the Turing Award addresses and put a lot of things up there that are AI complete. He thought the #1 problem was massive parallelism. The Gartner Group, they talk about things like automated speech translation, pretty interesting problems like that. #2 on their list was parallel programming, of things that would really change the world. And, you know, John Hennessy, who's supposed to be, he's, you know, on your board, he's supposed to be circumspect as the president of Stanford University. He says, look, this easy use parallel computers, this is a hard problem. This is about as hard as anything that computer science has faced in its history, and that's what we're proposing to solve this time. So when we think about projecting the future, we think about the context of what things will be like. We're not talking about 2 years from now, but 7 or 10 years from now. Well, our friend Luis, I believe, coined the term the data center as a computer, and that's our perspective too. The really interesting things for the servers of the future are warehouse-sized buildings, and then the client is the iPhone or the Android at the other end. So those 2 extremes of computing is what we think is the new client-server computing. And that's what we want to be thinking about, applications in those technologies. I'm not more interested in the extremes than in the middle. So the technology, what's going to be happening? Well, certainly flash memory is an exciting technology, obviously in cell phones, but I think we'll see in this next year or so flash memory popular in servers. And our actual new level of the memory technology happens pretty rarely. I think all these things you read about, well, what things actually happened in my career in my 30-ish years here? Well, you know, core memory, magnetic core memory got replaced by semiconductor memory, fiber optic cables, you know, that was a new change. A lot of the other stuff you read, holographic memory, all these other things, CCD memory, they never made it. So there's maybe we're going to actually see flash will actually be another level of the memory hierarchy for lots of computers. We're pretty excited, especially in the RAD lab, about software as a service and this cloud utility computing. This smells like a new thing that's going on. Instantaneous elasticity of computing available for anybody with a credit card, what we call cost associativity. Using 1,000 CPUs for 1 hour costs the same as one CPU for 1,000 hours. We've never had that before. And scaling, not only scaling up, which we've kind of had, but scaling down. We've never had scaling down before. Why, if you're going to build a big data center, why in the world would you make it smaller? Well, to save money and save power. So these are going to be forces that will be happening this next decade as well. Since a lot of companies gone out of business with that bet, why won't we go out of business this time? And we're kind of, and I'm not, you know, basically knowing the history, I'm not saying we're going to solve this one for sure. I just feel as researchers, we're being called upon in this time of need to stand up and really take a hard crack at this problem. So I think researchers, especially those of us who get government funding, or I guess used to get government funding, I guess we feel an allegiance to the industry at this time of need, and we need to stand up and help. We need to try. That's what I think I want to say. So why do we have a shot? This is the first time there's been no killer microprocessor out there. Nobody is building the 15 gigahertz, 100 watts microprocessor that's going to make all the programmers just ignore all the work you did. If you want to go faster, it's got to be parallel. There's no question about that. So that's never been true before. The other way this may work is, which, you know, wouldn't break your hearts, would be the utility computing, cloud computing services approach. That's the only way we're going to figure out how to use these things with millions of users using them. But that seems like that's got a good shot. In the past, it's been startup companies working on it. This is the whole industry, There's no company in the computer industry that's said, well, we're going to pass on parallel computing this time. They're all trying to figure out it, so there's more people working on it. I think the open source movement is more important commercially now than it was in the past. Perhaps they will respond to the ideas and embrace them. Perhaps, you know, this will be a good test for open source, whether they'll take advantage of this. Technically, a thing that we haven't had before is if we think about single chip systems, single socket systems, there's a lot of stuff you could do inside a chip that wouldn't be economical if we're talking about hundreds of thousands of chips. So maybe that'll help. We're pretty excited, as I'll say, is for those of us who want to build prototypes of systems of the future, including novel architecture. And a bunch of us used to try and build chips, which was very painful and very, very slow, and it'd take you 4 or 5 years, and 3 months after you got it working, the programmers would tell you what was wrong with it, so then you go back 4 or 5 years later, and it's a slow iteration cycle. Field programmable gate arrays allow us to build credible, but slow, but credible computers that can have interesting characteristics, I think are convincing enough that you could influence the real products of the future. And this last thing is, I was involved in the RISC ideas, and the big thing we're trying to convince people is that people will be willing to recompile their programs. No, they won't. Yes, they will. Okay, well, this time industry is pretty open to new ideas, right? They bet their future that someone's going to solve the parallelism problem, so more cores equals more performance. They're pretty receptive right now to people who claim they have solutions to that, so it makes it a little bit easier to technology transfer. All right, so that's the context. What about what we're doing? 3.5 years ago, a bunch of us started sitting in a room from all kinds of parts of the Berkeley campus and Berkeley environment, from embedded computing down the hill at the Berkeley Wireless Research Center to supercomputing up the hill at the Lawrence Berkeley National Labs. And we all got together and started talking about, wow, this is coming. What's the implications of this? I think we spent the first year just agreeing what everybody meant by the same terms, because every community had their own variation of these things. That led to this Berkeley View report, which for technical report was pretty rightly read, and kind of obvious, I guess obvious now. It seems surprising then that what's the goal? Is to make it easy, that is productive, to write efficient, that is power efficient and fast, programs that are at least as correct as sequential programs. They got to be portable, not unique to one computer, but move between parallel computers. And, and we think the most cost efficient point, power efficient point, is lots of cores per chip. And these things got to get better as you add more cores, and they're going to get added every 2 years. So when you put all that together, that's a pretty amazing goal, but I think that's the goal that as the research community we have to shoot for. And wow, that's some goal. So what's the big idea of the Par Lab? Well, no, we haven't got a big preceding idea. I think what we're going to say what we're doing is we're driven by the applications. And if you look at a lot of the projects of the past, often people like me will say, hey, I know how to solve this problem. I've got this idea of hardware design, and we're going to make the whole world rethink how they do software to match my hardware. And we'll spend almost all the money of the project on the hardware because it takes a long time to get working and stuff like that. So, or it might be a language thing. I've got this language, and this language is the right way. There's something about computer science that we have faith that if somebody just invents the right language, any problem can be solved. And we haven't solved all the world's problems because we just haven't invented the right language yet. So we got so somebody will come in and invent a language, then we'll build everything about it. So we're not doing it that way. What we're going to do, instead of, the hardware's finally working, let's hire some undergraduate to build a global climate change program in the last 3 months of the project, will actually be driven by real applications people who are real experts. And so instead of us doing the old wrong problem the way it was done 15 years ago, we'll be at the state of the art by somebody who knows what they're doing. And so we're going to let these applications and application experts figure out what really helps them, and they'll tell us which of our ideas are really big. And so I'll tell more about the process and who people involved, rather than where's the big idea that you know is right. Some other parallel centers already know what the big idea is, and they're betting a lot of it, on their hardware mechanism or language mechanism. Well, that's not the way we're taking it, but I'm really glad there's lots of centers working on it because it's a really important problem. So I'll show these 5 themes of applications, some design patterns, our 2 layers of software and operating systems and architecture, and then diagnosing what's going on and turning it into this colorful chart with our applications at the top in some purplish color. We've got a 2-layer approach to software, what we call a productivity layer and an efficiency layer. That's the green and pinkish things. At the operating system and architecture at the bottom is to support those goals. Correctness spans lots of layers on the right, and diagnosing on the left. So I'll kind of highlight that as I go through the talk. So applications. it's pretty depressing. This won't happen in this audience, but in other audiences, a conference I'll go and they'll talk about the future is multicore, and they'll say, who needs 100 cores to run Microsoft Word? And you hear a question like that, and you kind of wonder as an educator whether we failed in computer science. So the outer limit of all of the best thing we can do with computers is Microsoft Word. Right? So that's a very, I think there's a, you think about it historically, I think the technology we built was so cool, it was okay for us not to know anything about applications because it would help everybody, right? And so now that we actually perhaps better get more in touch with applications to be able to innovate, a bunch of us don't know what they are. Also, we use Word. Maybe that's the application. That's the killer app for Multicore. So we think there's a lot more exciting software that's been written yet. And so we wanted to find these experts. The way we did that is we went on the campus, lots of smart people in the Bay Area, and find somebody who was really enthusiastic, really needed a lot more horsepower than they could get today, knew what they were doing, and we wanted to get a variety of ones. So these will give you examples. These are the ones we started with. Probably still the biggest surprise to me is there's people in our music department at Berkeley who need more cycles. They are desperate for more cycles. I thought they were music professors, didn't barely know how to use a computer. These are, a lot of them technically savvy. David Wessel, not only do they need a factor of 10 or 100 more cycles than they have today, real time is serious for them. Our friends in graphics need a lot of horsepower, but actually if it doesn't look that good, our eye will kind of hide that if a couple of slides that way, and not our ears. Our ears can hear imperfections pretty clearly. Where he used to work, he said 3 clicks in electronic performance and you were fired, right? So it's a high standard there. He has this idea of a 3D sound system. That's this example they built with a speaker company, has 120 tweeters on it. Seems like the type of thing ought to be around here somewhere. Recreate the symphonic experience right in front of you. Because it's about hearing, he actually works with hearing aid companies as well to help you hear better in general and hear music particularly. And I think most of the music professors are performers as well, and he's tired of being bound to keyboard interfaces. He wants much more interesting novel interfaces to compose much more interesting music. So it's been a surprising and interestingly demanding application. Plausibly, especially at the client-facing thing, what performance means in the future is more responsiveness rather than some other kind of measure of performance. So how long does it take me to do something? That's the way we should be judging, which is closer to kind of a real-time evaluation of a system. We're also working with people in health. According to American doctors, the problem in the United States isn't the doctors, not the hospitals, the problem is we don't do what the doctors tell us to do. So suppose what happened, you had your body scan, you sit there and you meet with your doctor, and he says, this is what your heart looks like on the left there right now, but the way things are going, if you don't take this medicine or you don't change your behavior, it's going to look like the one on the right. And as you might suspect, that little red constricted thing, that's really bad. So perhaps if you saw your body and your doctor told this to you, you would do what the doctor said. So how big is coronary artery disease? It's gigantic. Just in the United States, 72 million have high blood pressure, 16 million symptomatic, 500,000 deaths a year. This takes a lot of cycles, lots of interesting things. It runs on really big computers now. Could we get it to run so that something you and your doctor could take a look at in privacy and feel comfortable? Those of us who have cell phones with a lot of flash memory in it probably have a lot of images. Labeling all of those would be a pain. Why not search based on images? So this idea that was started first by Intel was you give a couple examples, those 2 images of sisters, can we try to photograph with those together? And it uses support vector machines, machine learning, to try and train and find the images. So that was a content-based image retrieval. We've got speech experts in Berkeley. One of them is really good at meetings. In a meeting room with this kind of noise, can you understand what's going on? Wouldn't it be nice if you went to a meeting and get a diary, that's the meeting diarist, where it would list approximately what everybody said, identified by speaker. So he said, oh, Luis said something last time. What was it that he said? And I think it had this, and you'd try and find it that way. For those of us who are on large telephone conferences, wouldn't it be nice if there was kind of a closed caption version identifying the speakers going along? So we think advances there. And finally, a lot of those were media-oriented. We wanted something more like an application or a set of drivers that was different from that and closer to home. So we think of how could a browser take advantage of multicore? Can we make the browser experience, whatever the computation piece of that, much more interactive? And then, since a lot of the Web 2.0 apps are being downloaded over the internet, as you guys well know, what would be a parallel scripting language so that all the people who develop Web 2.0 apps would be writing parallel programs, whether they read it or not? Is there a way to do that? So if you kind of buy those applications kind of down the road, what would I like to have? Well, since you actually take your cell phone with you everywhere, and what you could do is take a picture of your plate before you ate and afterwards, and if it had a sensor, you might be able to weigh it before and afterwards, so it would really know how many calories you consumed, not what you said you consumed. And since you carry it with you when you exercise, it would really know how much you exercise rather than how much you said you exercised. So and when it was time to eat, it might say, well, Dave, you might want to order that salad instead of the free pizza here at the Google cafeteria. And because this is what you're going to look like if you keep eating that way. But the real killer application for me would be is you put your iPhone in your shirt pocket, and when this guy comes up to shake your hand that looks oddly familiar, but you're not quite sure, say, oh, that's Luis Barroso. You worked together, you did a couple of papers together in a conference several times, and he supported your bike ride. Don't remember to mention that, and it whispers in your ear whoever it is, and you just sound so smart. And for me, I would. If there was a name whisperer application and it would get better every year with more cores, I would buy the new one every single year. So, but the idea here is that if you think about the PC, some people bought the PC back in the early days, the Apple I, was because they wanted to write Visual Basic programs, or basic programs, right? So that probably wasn't a lot of those. So, but what the killer app was spreadsheets, right? Somebody came up with and invented the idea of a spreadsheet, and everybody, that sold a whole lot of PCs. So the parallel computing bet isn't that you have to make all the software in the world run well, that somebody will come up with some killer apps that'll need a lot more cycles than we can get today, and that'll attract people to want to buy newer machines with faster and faster. Or, a way to think of it, if that works, if we can do that, if as a field I can figure out a way that apps need as many cycles as need, and we can figure out a way, you just add more cores, everything runs faster, and if that'll last for the next 20, 30 years, we're in Fat City, right? That would be a wonderful world to be living in. All right, so that's the apps that are going to drive what we do. We did this thing in the Berkeley Review report that said, and this is a relatively controversial claim, when we talked to friends in high-performance computing, they said, look, there's about 7 things that are going to dominate high-performance computing. And so that, because there were 7, they got called the 7 dwarfs. So we started off from that idea and looked at a whole bunch of other areas: embedded computing, desktop computing, databases, games, AI, machine learning, computer-aided design. We said, do these dwarfs apply? And a bunch of them did. But there were others that weren't there we needed to add. So the first 7 columns there in this temperature chart, red means it's really important for these applications. Yellow and green are milder, and blue, they don't really matter very much. And you see this checkerboard pattern which led us to these dozen things. As we looked at these 5 applications, do these things apply? And basically they did. So a fairly controversial claim is, although the data types will differ and there'll be lots of different data structures as well in some of these applications, these things will find themselves at kind of the bottom layer of a lot of software. So if we could figure out how to make these types of things run well in your programming language or in your machine, that would bode well for the future. So that's our themes that way. Now, what about the software, which is really the heart of what we're doing? And I'll just have to give you a quick overview there. So since lots of types of programmers can use computers today, not just the people in this room, we're splitting it into 2 pieces: an efficiency layer. The 10% of today's programmers are building the operating systems and libraries that are really after quote-unquote bare metal efficiency. They don't want to give anything up. And then for the rest of us, for domain experts, they have to be able to program these computers, and we'll provide those frameworks for them, but they're more interested in productivity and not getting the ultimate in performance there. They like to get good performance. Primarily what we're saying is productivity people need to scale up. As you add cores, it gets faster, but the efficiency per core doesn't have to be spectacular. The efficiency layer people probably want the efficiency per core to be good as well as scale up. And then the big challenge is composition. How do we compose things together so that they're useful? So as I said, this is kind of what we're trying to do rather than what we've done. Kaushik Sen, who's a younger faculty, done interesting things with correctness and testing. He is thinking about, in terms of productivity layer, making it hard to express problems that will have non-determinism so they can still get their work done but not get them into holes. But we're going to have to put a lot of things in to allow the efficiency layer, all those nasty things that can happen, but maybe we can do things with testing and verification to try and help that. So an idea that we had good luck on sequential code is verify what you can and what you can't, automatically generate test cases to exercise those. What about compilers and code generation? Well, these days, getting performance, you talk to the architect, they don't know how fast stuff runs. Nobody knows how fast stuff runs. So we're in a very weird era where how in the world can compilers figure things out when no human being can figure it out? So the response to that is what's been called autotuners. They actually search the space. They try things and see which is faster. This particular example, it was when you were to block something, how many rows and columns, and the little red square at 2 rows and 4 columns turned out to be by far the highest performance in that temperature chart. How could a compiler have ever figured out? There's nothing obvious about that. So this idea is you generate a lot of variations and you try it on that particular machine to see what runs well. So it's experimental code generation. And there have been many successful attempts at that, particularly for sequential computers. And we're starting to see something for parallel computers. So here's an example of 4 multi-core systems from a variety of makers. These are very different. The cell is, the Cloverton and Opteron are very similar from Intel and AMD, x86 out of order execution, prefetching kind of the conventional wisdom designs. Cell is very different, designed for the PlayStation. The Niagara from Sun was designed for very thin servers, and you see they have much lower theoretical performance in terms of floating point operations at that bottom line with Intel at the top, and much lower clock rates for Intel, for example. For the Sun example. But what happens when we ran naive versions of these programs on those computers? First of all, for Cell, it's so unusual, there's no naive version that runs on Cell. But look how little performance we got from the naive versions on the Cloverton. It's 1/75th of the potential performance. By auto-tuning, we could get things better. Exploring the space, trying things out, we could get things running a lot better. And much bigger speed-ups, factors of 1.5 to 3, then you'd never expect that from a compiler, but auto-tuning, it knows more about what's going on, doing more experimental things, so we think that's going to be a promising vehicle here. Now, auto-tuning takes pretty smart people in architecture and applications. We've got recent results using machine learning, kind of from my Rad Lab hat. What it's trying to do is learn relationships between a set of optimization parameters and the performance. So we try these, here are a bunch of parameters, here's the performance we end up, we see these 2 spaces, can we find these correlations and figure out what's going on? And we were able to do that for one of these kernels, a stencil kernel, and get within 1% of what the expert was able to do in a lot less time because we're using the machine learning techniques. So this is promising because it's pretty hard to build these auto-tuners by hand. Can we use machine learning technology to help us automate the creation of auto-tuners, and so that this could be a more general technique. So we're doing auto-tuning, not compiling. We got these 2 layers rather than 1 layer, and libraries go ahead. What about closer to where I live at the bottom of the stack? Well, small is beautiful is going to guide our designs. We think the most power efficient and cost efficient point is modestly pipelined CPUs with not a lot of dynamic stuff in it because that's wasteful in energy. We're thinking about something more reconfigurable in the memory hierarchy. Sometimes it's local store, sometimes it's a cache. And really fast partitions you can do technically today. Operating systems, deconstructing them, going back to virtual machines, and if we're going to have this ability to partition the chip very efficiently in hardware, can we provide that partitioning via thin hypervisors to applications so they can get full software access, this bare metal efficiency? How are we going to prototype these things? As I previewed before, we're part of this RAMP effort. What did RAMP stand for? All the R words blend together right now. See. Research Accelerator for multiprocessors. And this is, FPGAs have get bigger by Moore's law. So you can now, if you're trying to do multi-core, you can put a lot of cores in one FPGA, which makes it a much simpler problem to build than if you were trying to build one processor out of a lot of FPGAs. So we put this to demonstrate the idea. This is a 1,000 processor system in one rack of equipment. And since we did this prototype, Chuck Thacker of Microsoft helped us design the next boards, and there's a third-party company selling them, and there's a consortium building software and gateway around it from a half a dozen universities. So we think being able to emulate using FPGAs will let us explore the space in a more interesting way, even if it runs slower. How about in terms of the performance evaluation? So we think we're going to have to do measurement to be able to help that out. And then the questions are, what do we tell the efficiency level programmer? Well, we can try and explain what fraction of the machine he's doing and why he's not getting all the bandwidth. But for the productivity level programmer, it's got to be the higher level of abstraction. So an idea we're kicking around is maybe we need to come up with the moral equivalent of IEEE floating point standard. We need to have a performance counter standard that everybody has to run so that we can have portable debugging performance tuning devices across machines. That and if we had it, then the operating system could use it to more efficiently schedule these machines. And our argument is, and of course, whether you know it or not, the performance counter thing is this thing that hardware architects put in to see how it's working, and they don't have to work because nobody's supposed to care about them. So we should change that culture. And look, if we're going to get 20% more performance as a result of measuring, if that's true, why can't you spend 10% of the resources on that? So that's been the justification in the past, to put in some wild and crazy branch predictors and stuff like that. Well, we get more performance than the resources is a good idea. Well, I think in this new era, where we don't know how to program these things, better measurement's going to get a much better return than transactional memory and all these other crazy ideas that people are trying. Who knows if these are going to work? Measuring what's going on, accurate things, is going to make things run faster. So this is something we're going to pitch, and we're going to build it, right? This ramp will let us build it. We'll be able to have the world's first implementation of this new standard, or we'll prove it on this implementation that runs real software and demonstrate it, the value of it. Hopefully that companies will embrace it. So kind of putting the picture here, why are we getting these experts to work with us? Well, we're going to help them get their software running on the latest computers, and we're going to be able to afford to get a lot of them, and we'll even, because we have close to Silicon Valley, we can get stuff before it's a real product to be able to use. And in return, they let us use their apps to innovate in the architecture and operating system, and they're going to, kind of interestingly, RAMP might be the best place to run computers, run your parallel program, because you're going to have as many cores as you want, and it's going to have as much instrumentation you want. You'll know more about your program on RAMP than you'll know on any computer in the world. It just runs slower. But since you want to port your things to a lot of platforms, if you run it to all the Intel and AMD ones, and from NVIDIA and ours, you get kind of the best of both worlds. You can run it on lots of real things, and then you'll get these insights from RAMP, and we'll be able to build better computers, demonstrate them for the future. All right, so I'm going to pause. This is the summary of the kind of the Power Lab. How do we get here? What are we working on? And then I'm going to give myself, since I spoke plenty fast enough, despite the 10-minute delay, to do the performance model stuff after this. But I'll take questions now. Is this an easy thing where people just raise their hand, or is it? Okay. Yeah.
So you talked about software as a service, and the question that comes to mind is why that is not a killer application or a killer user scenario for the computing power. Why we need to come up with new applications that can use the computing power.
Yeah. Okay. The question: given software as a service, aren't we done? I believe. I can tell you right now, in the city of Berkeley, I don't get cell phone coverage in parts of Berkeley. In fact, there's a big city council debate whether they'll put up more cell phone towers. So I think if we had ubiquitous communication anywhere I went, there'd be an argument that I'll have a thin thing, the cloud, but there's going to be hundreds of gigabytes of flash in this thing. I think there'll be times where I'm going to want to be, or there'll be low latency things like speech recognition and stuff like that. I believe there will be a case for local communication at all times, as well as the future. I think the application mode of the future is things that you guys do here, right? It's in the cloud and it's on the client. It's in the data center and it's on the cell phone. So I think there are an interesting challenge will be, can we figure out how to make the client's stuff run fast and take advantage of more things in the future, as well as in the cloud? And I think that's, at least as researchers, if we can do that, it's great, right? But kind of leaving the researching aside, as from a commercial perspective, the inability to take advantage of multi-core, many-core may be an accelerator towards putting things into the cloud, right? If we can't figure out how to, if companies like you can get much more cost performance out of multi-core than people can for laptops, maybe that will be shoving things into the cloud. Question? Oh, I'll go back and forth, okay?
What will the memory hierarchy look like in a few years? Is the memory bandwidth scaling at the same rate as the number of cores?
Okay, the question about memory hierarchy and memory bandwidth. So basically, if you look at the 25-second summary of computer architecture last 25 years, basically the people who call themselves computer architects got to pick the packaging technology. And all these startups in this area would do very innovative packaging technologies and very innovative memory faces. And then the person making the decision said, do I want to bet my baby on whether that packaging technology works? And the only way we're going to know that is if it's in the field for a few years. So more or less everybody said, I think I'll just go build a bigger chip, right? And put a lot of caches around it so it doesn't need innovative memory interfaces. So I think going forward, we're probably not going to be able, we won't be able to get away with that. So we have to have, to have a lot more cores, we're going to need more memory bandwidth off the chip. And I think, well, there's, I think 3D packaging, more innovative ways to interface with memory has a lot more performance in there. We've just never explored them. I think we're going to have to do that. So I think the good news, even though it's hard to find the evidence that there's the ability to get a lot more bandwidth to memory, I believe it's there. As I said, I think the flash memory is going to be very exciting. So kind of a related question is, what about I/O? Boy, if we get a new level of memory hierarchy that's not mechanical, just like I still have colleagues who use the word core when they refer to memory. It's a possibility you use the word seek time and rotational delays, and people won't know what you're talking about in 5 years from now. So I think there's some reasons to. Flashes and phase change memory is a real reason for optimism for I/O, and I think there's innovative ways to go to memory right now. I think another kind of, on the memory hierarchy, what's going to look like, the cell processor we used did not use caches, it had local store, and it has a VLIW instruction set, really a pain to program for, but the funny place we are today from efficiency level programmers' perspective is architects put caches in to try and make it easier for programmers. You don't have to worry about the memory hierarchy. Today, at the efficiency level, people are trying to reverse engineer all this hardware mechanism, prefetching and stuff like that. So it's a very weird state. We're putting hardware in supposedly to make it easier, but it's not easier. They're trying to reverse it. If you just put a local store in, that's easier. I know what it does. I can put in DMA that's predictable and things like that. So we're looking at a memory hierarchy that's flexible, that sometimes it's caches, maybe for productivity level programmers, and sometimes it's local store for the people who know what they're doing, because local store is kind of easier for them to reason about and use. That's another long answer. Yeah.
So you're talking now about microprocessors, and a lot of the performance gains you get are from interconnects. But what do you think about interconnects?
The question's about interconnects. So there's on the chip and between chips. So on the chip, power is the big, where are we today? Power is what architects worry about, not transistors. You can put more transistors you can turn on. So we could be, this is what a strange word. We could be thinking about structures that you put on chip that use up transistors and gates and all that stuff that are turned off a lot of the time, that you only turn on when you need it. So we're thinking of having that the power efficient way on the chip will have many dedicated networks on it. That'll be more power efficient and more bandwidth per effective watt as a way to connect on the chip. Off the chip, the serial line technology is very exciting. I have colleagues who are very interested in optical interconnects. So optical on the chip in particular, so when you go off the chip, you don't have to have that electrical optical connection. So there's arguments in there. So that's promising. And of course, you're all here today because Andy Bechtolsheim gave Larry and Sergey some money to start. Andy Bechtolsheim is working on interconnects in the data center, thinking there's a opportunity to do data center interconnects much more efficiently than the Ciscos of the world where he used to work. So I think there's a lot of pretty interesting sets of challenges that have to do with power on the chip and probably power and some of the data center things off the chip in the data center in interconnects.
I wanted to suggest that we move on to
Yeah, okay, all right. Yeah, I'm not going away, but I'm going to get to this performance model. I've given this talk 3 times, and every time I never got to this, so we're going to go, this time we're going to do it. Okay, so why do you need a performance model for multicore? Well, like I just said, there's no consensus on, a few years ago, everybody built more or less the same microarchitecture. Everybody was out of order, branch prediction, all the stuff, it didn't matter the company, you knew what was inside. Boy, the world's different today. And right now, to get a lot of performance, hopefully that will always be true, you got to be really good at the application and really good at architecture to understand what's going well. Not very many programmers know both architecture and the applications, and pretty much performance is the reason many people are worried about multicore. So to give you an idea of the diversity, here are the 4 machines I talked about before, kind of graphically. These are all dual socket systems, so all of them have 2 things there. The Cloverton is actually done with 2 independent chips in the same package. That's the socket, and it's a shared bus interface. The Opteron's a more modern design with the bus going to the DRAM. They have separate DRAM interfaces. The Sun has this very thin cores, very low clock rate. So 16 thin cores across these 2 sockets, each 8-way multi-threaded. That's a pretty radical design. And I mentioned about the cell that has local stores, lots of these SIMD thin designs. So all over the space is where things are today. I don't see any reason that this will converge shortly because we don't know what the best thing to do is. So this new model was focusing on these dwarfs. I mentioned it before. I'm going to present the floating point version, although we've thought about others today. And so this new performance model is not trying to accurately predict how fast it's going to run. It's what's called a bound or bottleneck analysis. So we're trying to figure out where the bottlenecks are. The idea is, from either an architect's perspective or a programmer's perspective, what they're interested in is why can't this program run faster, and we want to know what the next bottleneck is you have to get through to go faster. So that's what we're doing. And right now, these examples are going to assume the parallelism and load balancing on issues. We've talked about that. We've thought about that other, but we're not going to show that in these slides today. So, what's the bottleneck for floating point programs? Well, peak floating point performance is a bottleneck. And a lot of the applications today, everything doesn't fit in the caches for the applications we're talking about. So one of the key figures of merit that we're going to use that's going to drive this model is what we're calling operational intensity. And this is the average, for this set of examples, how many floating point operations do you get per byte that goes to DRAM? This is after going through all the caches. So it actually gets all the way out to the memory system. For every byte, how many operations do you have to do? So that's, we think, is an interesting figure of merit for these dwarfs. So now we're going to, this is not only a performance model, it's a visual performance model. So the y-axis is going to be gigaflops for floating point programs. That makes sense. And it's on a log scale. So you can look that up, actually just look that up for a computer. In this case, the red line is at 16. This means that's the peak floating point performance of that hardware, 16 gigaflops. Okay? Now, what we're going to make the Y scale, the X scale is going to be operational intensity. So this is the number of floating point operations every byte that goes to DRAM. Well, if you think about that, it's the number of floating point operations per DRAM. Well, we can plot another line that is the memory bandwidth. Since gigaflops per second divided by flops per byte is gigabytes per second, that's that 45-degree diagonal line. So because it's operational intensity at the bottom, right? It's how many flops per byte. And the memory speed is bytes per second, so you'll turn that into a 45-degree line that intersects with the peak floating point performance. So this is the model, right? This is the model that we're saying right here, is that slanted piece, and the flat piece is what we call the roofline. That's where the name came from. So depending on the operational intensity, you can't go any faster than those 2 lines. You can't go faster than the peak gigaflops per chip. And the memory bandwidth in the area where you have few operations per byte going to DRAM, that sets another limit. Okay. So far, so good. So what we call the point where those 2 things meet on the roof line is the ridge line. And the ridge line is the minimum operational intensity where you get the peak performance, right? If you're to the left of that, or if you're to the right of the ridge point, that means you have enough operations per byte that you're computation bound. So that line would intersect, run it, you can think of that as a pole that runs into the roof. Well, if that's your operational intensity, you could theoretically get the 16 gigaflops performance. If you're memory bound, if you're left to the ridge point, then the memory performance is going to limit what you can do, and you won't be able to go higher than that slanted part of the roofline wherever you intersect, okay? So it's a simple model, and we're looking for bounds and bottleneck analysis. Gigaflops on the left, operation tilts on the right, and we get this roofline with ridge point. So now the question is, well, all right, that's an interesting idea. What do the rooflines look like for these multi-core computers I told you about? And where is the real operational intensity? Is it way over to the right, where that should be easy, everything will be compute bound, or is it way over to the left, where everything's memory bound? Okay, next slide reveals all. So those are the 4 machines we showed the slides before, with the Intel Cloverton being that green line, pretty steep slant, Barcelona being the red line, the Cell Blade from IBM is the blue line, and the Victoria Falls is the purple line there. And so look at that Cloverton. Boy, the Cloverton has almost no flat spot there, right? It's almost the whole, most of the region that I've plotted here in terms of the flops per byte is memory bound. And that's true, right? The ridge point is 6.7 double precision floating point operations for every byte that goes to DRAM. Or if it was an 8-byte double precision floating point operator, that's like 56 floating point operations for every double word that you read from DRAM. So that's a lot of operations. The Barcelona is only a little bit better at 4.4 flops per DRAM. On the other hand, when you get to the Cell Blade, it's down to kind of 2/3 of a flop per byte, and at Sunsday, amazingly, 1/3 point per byte here. So now where are the operational intensities for these kernels show up? So these are real ones, sparse matrix, the stencil, a structured grid code, and FFT. And those are along the left. Its operational is 1/4, 1/2, about 1, and 1 2/3. And you can see that these lines, where they line up. So even though the peak floating point performance for the 2 leftmost lines are much lower than Cloverton and Barcelona, because they're memory bound, but the Cell and Victoria Falls have higher memory performance, in practice you get more performance out of it. So architects, if you see a roofline for a computer, you can get an idea what you need to do to get the performance out of it, right? How hard is it going to be? And I'd say a lot of the things we look at are less than 1 flop per byte that goes to DRAM. So that's the peak performance. What happens if you're below it? Well, it turns out what you can do is you can try and figure out what the optimizations are that are commonly done for that type of program and plot them as ceilings below the roof line. And then the operational intensity is going to tell you which ones to do. So let me show you that. So if you were cared about floating point performance, one of the things you want to do is at the top is have an equal number of multiplies and adds. There tends to be an equal number of floating point adders and floating point multipliers. So you want to have an equal number of adds and multiplies if you have that option to get the peak performance. So that's the first ceiling there at the top. If there's an imbalance, you can't get all the way to the top. Now on these x86 architectures, what this is about, they have these single instruction multiple data operations that you can do 2 double precision floating point operations in 1 instruction. If you aren't using those instructions, you can't go above that ceiling. And then these will execute up to 4 SIMD instructions per clock cycle. If you're not executing 4 instructions per clock cycle, you're going to be at the next lower ceiling. So these are examples of computational ceilings. What would ceilings look like for memory? Well, those will be these slanted ceilings. So prefetching is very important to get the peak performance out of the memory system. So if you're not prefetching, it comes down a level. And then on these dual socket systems, if you're connected to DRAM, if you're going through a chip to somebody else's DRAM, that's slower than going to your own DRAM. So there's a NUMA effect as well. So if you get a colorful version of this, kind of the yellow memory thing, and the blue computational thing, and the intersecting area, which is green, yellow plus blue, is where you have to optimize both computation and memory system. So what the idea is, there's those 4 lines we saw before for the 4 different kernels. If you're way over on the left, don't even have to worry about the computation stuff. You're limited by memory, so just worry about prefetching and NUMA. If you're in the middle, you don't really have to worry about SIMD or don't even worry about multiply add. You're never going to get there. Just try and get the instruction level parallelism there. So depending what your operational intensity is, you look up and see what you should be working on. And it tells you what you don't have to worry about. And more importantly, what's the best you can do? Is if you're in the second one and you've got 7 gigaflops per second, that's pretty good. But even though the peak gigaflops is 128, still 7 is about the best you can do. Okay, so this is the performance model. So where are we on this? Somebody besides us actually used it. That's always an unusual test for academic research. Is number of users exceed the number of authors of the paper. So this person did a summer intern, and he used 2 different kernels. There were financial kernels, PDE solvers, on 4 very different multicores. GPUs, well, standard Intel processor, the upcoming Larrabee, and 2 NVIDIA GPUs. And the first version of this PDE, he looked at the bandwidth that fit in the L1 cache, so he didn't have to do any optimizations for it. The second one didn't fit, so he could use the Roofline to help figure out what blocking he needed to get the peak performance and what he could get. We're looking at non-floating point kernels. Presumably, a lot of you are interested in other things like sort and graph traversal. And there's a whole, we've just scratched the surface. There's a lot of architectures, a lot of algorithms. Particularly, we think this will work for I/O, which we haven't, worked on yet. But so we're pretty excited right now. So let me wrap up in just perfect timing the talk and see if there's time for more questions. So why are we doing this? If nobody can build a 15 gigahertz, 100-watt uniprocessor, if you can, there's a big market for you out there. And, the industry has bet its future on this. We're used to getting more performance over time. Maybe we can keep selling computers, even though computers don't get faster, but we don't have a lot of experience at that. I think from a researcher perspective, you can argue this is the hardest problem in 50 years. That's both this tremendous upside opportunity and a tremendous downside if we don't. And not only that, from a research perspective, here's the chance to reinvent the whole hardware-software stack. I don't know when the last time you had a chance to reinvent the whole hardware stack, but right now, if you could solve these problems, you could change a whole lot of things if you can really deliver on that. So in terms of, are you part of the problem or not? So it's not failing this time. It's not trying. So are you going to be part of the problem or part of the solution? Okay. I'm ready for applause. Okay. Oh, I'm so surprised. And these are our sponsors, and if you wanted to learn more about the Roofline, Sam filed his dissertation yesterday. Okay, I'm ready for questions. Right on the button. Let's try, okay, first up.
How do you quantify composability in having fixed size, non-cache memories, or optimizing kernels is nice, but users have to compose them. How do you quantify what performance needs are there?
So I think in terms of the questions about how do you quantify composability, I think for right now, at this early stages, we have a bunch of interesting component technologies like autotuners and these kernels and all stuff. Can we put this together in an app and have the application still have pretty reasonable performance? Will that work at all? And then can some of our applications experts, like productivity level people, can they use those to compose things together and get pretty performance? So for right now, it's going to be the measurement, will it work at all and how fast does it run? Down the road, it'll be, well, how much effort is it? And as we said in the Berkeley View thing, there's a whole bunch of parts of at least the Berkeley campus and probably here, that does human subject experiments. Computer scientists pretend like you can't do experiments with human beings. It's possible because there's too much variability. Well, human beings vary all over the campus, yet they do experiments. So down the road, it'll be if we can get things that work at all, performance-wise and correctness-wise, can we do these experiments to see how easy it is for these tools to work? Can more domain experts use them, and how long does it take them and stuff like that? That'll be, down the road, measuring both how hard, performance sides as well as productivity is how long does it take, how many mistakes to make, stuff like that. Yeah?
You talk about reinventing the software stack. Lisp was 1960s, et cetera, What really are the odds that programmers are going to change their way of thinking?
The question is reinventing the software stack. Lisp, nobody uses Lisp. Is that Lisp was...
Lisp is far better than the...
Lisp is far better.
And we ended up with Fortran, we
Right.
ended up with COBOL, we ended up with SQL when there was
Right,
Prolog.
right.
We always pick the worst choices.
Always pick the worst choice. Okay, so this will get me, I'll try and restrain myself here. Let's see. The reason that we could invent the whole software stack is I characterize it as industry, if those of you know football, industry's thrown this Hail Mary pass, right? And it's late in the game, a football game, you're behind, what are you going to do? You throw the ball as far as you can. So it turns out it's pretty easy to throw the ball. It's the catching that's the hard part, right? So the industry is hoping somebody will catch it, right? And if you come to them and say, well, we can catch it, here's the changes you got to do. If you can really deliver on that goal of correctness and efficient and scale up and stuff like that, I think they'll consider all kinds of ideas right now. So I think we could really invent things. Now, in terms of, things have never worked, with my Rad Lab hat on, we've been teaching courses at Berkeley about Ruby and Ruby on Rails. Ruby is a pretty cool language. There are people, and they're getting real productivity gains. In terms of and we can do this in class. We have a bunch of undergraduate students who've never seen Ruby, never seen Rails, and they're building apps that they're excited about and deploying them on EC2 S3, and even getting some users in a semester. And how big are the programs? I think this is most thing. 1,000 to 2,000 lines of code. I never thought I would see 1,000 or 2,000 lines of code in my lifetime. It looks like something you'd say, well, it was 30,000 lines of code or something like that, and it doesn't really work. They seem to work. They have a pretty nice user interface. One person was trying to do medical records for boarding schools in third world countries. They had users in Senegal during the class. They had reached out and they were giving the evaluation. So this is a very productive environment. Ruby on Rails has its own set of advocates. It's not just the academic community. So I think there's reasons to believe of very innovative software systems are out there, kind of just like Lisp. Many people are advocates for Lisp. I think they're out there, and I think there's a chance for us to create the technology to make these mainstream. Could Ruby on Rails or a Ruby-like language, something like that, be the productivity language for multicore? What we need to do is figure out how to scale up the number of cores. So maybe Ruby's inefficient on one core, but it can use 100 cores. Well, if that were true, that would be a pretty powerful argument for Ruby, because I think unquestionably it's more productive, but everybody argues about scale or efficiency. So I think I'll cut myself off there. Luis, do you have a question? Yeah. Okay.
Slow a thread can you get away with? You've been looking at a bunch of applications. Some people would argue that practically it becomes very, very hard, and therefore, the productivity suffers after some threshold.
Yeah, so I think in the Berkeley View thing, there's this argument for heterogeneity, and it's just Allenbaugh's law, right? If there's some pieces that are more sequential and some pieces that are more parallel, you could be, this bound and bottleneck analysis is an Allenbaugh's law thing, you could be limited in performance by this less parallel piece. So I think there's an argument for having some faster cores. What's happened, I think, commercially, I think it's unacceptable for an AMD or Intel to bring out with a processor that would genuinely run some programs slower. That may be just too hard a business thing for them. Sun, on the other hand, did this radical thing and somewhat IBM too, a very skinny, slow cores that would run some programs slower. Now, I think I'm less worried about the business side of that than technically, right? If that's the most efficient, if we can figure out a way to use that and that's the most efficient point in MIPS per watt and things like that, my guess is going to be, and can operating systems handle that kind of scheduling? Schedule the pieces that are more sequential on the fatter cores and the ones that are more parallel on the thinner cores. I'd say kind of technically we could do relatively thin. I think this 5-stage RISC pipeline, we built that. Our version was like 30,000 transistors. So that's a very efficient point in technology. Maybe vector is pretty efficient. So I think if it's power, what's very efficient in power and transistors points, I think historically those have been. So I think that I don't see a reason to go less than that. And there's an argument for getting to that point. But what's the programming challenge is, historically it's always been, it's better to have fewer processors and fatter cores because of all the problems that come in parallelism. If we cut that Gordian knot so we can really embrace a lot of parallelism, then I think it'll head towards a lot of the skinny cores and maybe some fat cores because of the Allenbaugh's law thing. Go ahead.
What happens to the ability to find legacy applications that are out there that aren't parallel?
Yeah, right. Yeah, what happens to legacy code, right? And people ask academics, So I think it would be a mistake to come up with, it may be possible, it'd be hard, to come up with an architecture idea that could not run that code. It may be possible to do that. I would not recommend that. I think, I think you need to be able to run words of the world. There's a bunch of software I use that I don't think it has to get any faster, but I want to run it. So I think you have to keep running that. I think in the, if it was a startup model, business model, there's an opportunity in the next few years to automatically parallelize so that you can get some value out of 8 cores from legacy code. That's just not, or if I thought that was the path to the future, that we could automatically parallelize any code, including legacy code, and we'll get up to 100 cores, if I believe that, maybe work on that. But I don't believe that at all. I think we've tried that a whole lot. I think you may be able to get modest parallelism on a lot of cores, for a while, but once we get a lot more, I don't see how that could possibly, I'd be amazed. If that could work, of course, that'd be a huge breakthrough, but I don't think that. And so I'm not as worried about that, although it's commercially really important. It's hard enough without the legacy code problem. Go ahead.
In your list of applications that you're using to help drive the research edge, your explicit mention of distributed computing, and it seems to me that might be an area that could be overlooked with your ramp system where it's a single machine and you don't have multiple machines. And find applications that are defined by the network rather than just happen to be in the network itself.
So, I'm right now wearing 2 really interesting hats, and one's the RAD Lab, which is machine learning to make data centers easier, run easier data centers. So we're really, that part of us, like the Ruby on Rails, we're really interested in distributed applications and how to design them to run well, work well with machine learning into operation, all that stuff. So that's not so much, that's more the focus of the RAD Lab. The Power Lab is more focused on the client stuff. I think the technology we invent for the clients will carry over. So I think the auto-tuning work, I just can't imagine a future that auto-tuning, be amazed if you can solve this problem without auto-tuning, that there's so many unique things there. So I think there's in some of the programming layers and stuff, I think that stuff will carry over. But kind of at Berkeley, both of those things are going on. They're just, not, they're 1 floor apart. And so I think, but I think, the apps of the future will be across both of those things. So there will be distributed computing going on, research at Berkeley and the client stuff, but not in the single lab, if that answered your question. Yeah.
Last question.
Okay.
Do you have any thoughts on performance stability? In particular, what I'm worried about is, I changed one line of code, suddenly something that was massively parallel is now horrendously sequential, and just, falling off a cliff in every direction of source code change.
Yeah, the question is, what about predictability, small changes leading to unexpected consequences? I think there's this version of what the future might look like. The reason it's more promising is that we'll redefine what performance is. So I mentioned like responsiveness is another definition, but I think part of responsiveness, especially thinking about music, is predictability as well. So suppose what you could do is if you got a lot more cores, is you get a more kind of stable, more predictable system. It wouldn't sometimes it runs great, and sometimes it runs poorly. So, and I think there's borrowing kind of from the other lab there, the machine learning stuff. The machine learning is an interesting way to explore a much larger space than we would normally explore with real computers, and already in the auto-tuning, there's a lot of combinations. If we're going to run it on things, we have to kind of use heuristics. Machine learning has this interesting ability to kind of separate the wheat from the chaff and try and see what some of the fundamental principles. If that actually works, we've already thought about, because we could search a bigger area, we've already thought about performance and power. Could we get kind of predictable performance or more stable performance as you vary the input data sets or something, it doesn't fall off a cliff. So I think that might be an it'd be great to look 10 years in the future and see whatever happened, but I can imagine that's the way we define success. Sure, maybe it really didn't get this linear speed up that you expected from more cores back in 2008, but what you got was much more stable performance, or a lot of the time it was the responsiveness. Most of the time you're not using the cores, but when somebody wanted to use it, the distribution of response times was much lower. So that this responsiveness predictability, I think, is a really interesting way to potentially evaluate that. And we're really seriously going to look at both of those things, responsiveness, productivity. That might be the way that's going. Because, kind of my friends who've done this for decades, my good friend John Osterhout, who's now at Stanford, he did this for his dissertation. He doesn't think it's going to work. He thinks, you're going to fail. There's no way it's going to work. And so, and he's a smart guy, and I think there's a reason to bet against it. So, but maybe if we look at computer systems in ways we haven't looked at them in the past, there's certainly plenty of things we could do better than we do today. And maybe by redefining what people really want in new ways, that'll give us the flexibility to actually be successful this time and like the past. Okay, thanks.
Thank you.